All the rivers run into the sea, yet the sea is not full. Unto the place from which the rivers come, they shall return again. The eternal cycle continues, for without clouds there can be no water, and without water there can be no life. The sun evaporates water from the lands, the lakes, and the seas, and it rises as vapor to form the clouds that move above the earth. And as temperatures change, the clouds release their water as rain or snow, and it returns to the lands, the lakes, and the seas from whence it came. Stored in the atmosphere are over 3,000 cubic miles of water, and each cubic mile contains nearly 1 trillion gallons. Every day, 280 cubic miles of vaporized water are lifted into the atmosphere, and every day, 210 cubic miles fall on the sea, and 70 cubic miles fall on the lands to serve man and sustain his life. The need for pure drinking water has been the concern of man ever since the beginning. The location of lakes and the courses of rivers have always influenced the direction and extent of his travels and the location of his communities. The first public water systems were wells used in China before the Christian era. Men were no longer dependent on rivers and lakes alone for their supply of water. In the second book of Kings, we learn that Hezekiah advanced water technology by making a pool in the surrounding hills and by laying a connecting conduit, brought fresh water by gravity into the parched city. Later, the Romans built imposing stone aqueducts to transport water from distant springs to their growing cities, and parts of these systems are still in use today. Development continued through the ages, and by the middle of the 1700s, settlers who founded Salem in the New World built a gravity-fed town water supply system using hand-bored log pipes, while the town of Bethlehem in Pennsylvania had harnessed the steam engine to their water supply system, ending the age-old dependence on gravity. With the expansion of Canada, communities grew into towns and towns into cities, and by 1888, the city of Vancouver had constructed its first water intake on the Capilano River. From this beginning, the community's water department employed the latest techniques to meet the immediate demands of the growing population, as well as plan for future requirements of a continuously expanding community. More streets, more houses, more people, and the rapid expansion of industry called for larger capacity intakes to feed the growing complex of water mains which were spreading over the lower mainland. Larger mains were built to transport water under Burrard Inlet, which separates Vancouver from the mountain watersheds. In 1926, the Greater Vancouver Water District came into active being to acquire, supply, and distribute water throughout the lower mainland. Larger dams were built and storage areas increased, but without pause, municipal and civic development continued, imposing an ever-increasing demand for water on the Greater Vancouver Water District's administration. Huge high-pressure mains were installed to meet present and foreseeable requirements. With his associates, Dr. Cleveland introduced an imaginative water supply program which emphasized future development, anti-pollution, and complete watershed protection. Over the years, dams were built and storage basins created to hold excess runoff from the surrounding mountains. Today, the magnificent lions overlook the Greater Vancouver Water District's fully protected watersheds, dams, and storage lakes that are capable of supplying abundant quantities of pure water for domestic and industrial use. Greater Vancouver is located in the southwest corner of British Columbia's lower mainland. Comprising 563 square miles, it is bounded on the west by the Strait of Georgia, on the east by the Stave River, on the south by the international boundary, and the north by the magnificent Coast Range. Within these mountains are 3 uninhabited watersheds, having an area of 226 square miles. These watersheds, with their lakes and streams, are fed by the heavy mountain precipitation of rain and snow. By constructing dams with tunnels and control valves, water from these natural storage lakes is fed into the Capilano and the Seymour river systems. To supplement the normal flow of these two rivers, plus the Coquitlam River during periods of low runoff, 3 dams were constructed: the Cleveland Dam, the Seymour Falls Dam, and the Coquitlam Dam. These have created large artificial storage lakes of soft, clear mountain water, which is distributed by a complex system of high-pressure water mains throughout the Greater Vancouver Water District. To regulate water pressure and provide local storage for peak consumption, reservoirs are located in strategic areas. These are supplied by a combination of gravity feeds and pumping stations that daily move millions of gallons of water from storage lakes and reservoirs, and as consumption demands, from one reservoir to another. A master pressure reducing and control center located in North Vancouver is the heart of the system and controls delivery to the surrounding municipal areas that purchase water from the Greater Vancouver Water District. They receive it through metering and testing stations where municipal consumption is recorded and quality tested. Once it leaves the Greater Vancouver Water District mains, it enters municipally owned and operated systems for local distribution. A turn of the tap, and through these diverse facilities, water is brought from high in the mountains that are bountifully fed by summer rains and fields of winter snow. To evaluate the quantities of water stored in the mountain catchment areas, snow profile teams now travel 5 specific snow courses to measure the depth of snow and its water content. The long-term record obtained by these measurements will become invaluable as more dependence is placed on snow storage. This data will then be used by the maintenance and operating department to program the confinement or release of water held in the mountain reservoirs and behind the 3 large dams which form the district's major water storage. Coquitlam Lake mainly supplies the eastern areas of the Greater Vancouver Water District. The Seymour Dam, located on the Seymour River, is 1,400 feet in length. The dam forms a storage lake 4.5 miles long, containing over 5.5 billion gallons of water. This will be increased to 21 billion gallons when the dam is raised to its full height. Inside the dam is a labyrinth of tunnels, passageways, and cavernous rooms containing the machinery and instruments used to test, control, and screen the water, as well as operate the dam itself. Before water is allowed to enter the huge mains at any of the 3 dams, it passes through a series of fine mesh screens to ensure that no particles enter the system. This is particularly important during the spring runoff and during periods of heavy rain. Screening is one of the processes that ensures purity of water before it is distributed throughout the lower mainland for domestic and commercial use. Electric power is produced within the dam by a water turbine generator. This power is used to operate the pumps, valves, screens, and gates, as well as provide light and heat. Should the turbine generator fail, a standby diesel generator unit automatically cuts in and provides electrical power until the turbine has been restored to service. At the base of the dam are two large Howell-Bunger valves, which can pass 3,400 cubic feet of water per second to the lower Seymour River. They can be used to lower the storage lake should the need arise, and during periods of low runoff, they can release water for the fish which spawn below the dam. For a total cost of only $20,000 per year, the water is subjected to a second purifying process before being allowed to enter the mains for distribution. Each of the three main dams is equipped with a chlorination plant, which, under strict control, introduces minute quantities of chlorine to the water. A master control panel indicates and records the actual flow of water through the mains and the precise amount of bacteria-destroying chlorine that has been introduced. Water samples are constantly checked by trained operators to ensure the chlorination system is in proper balance and the recording mechanism in order. As conditions change, the introduction of chlorine varies proportionately. Thus, the exact balance of chlorine to water is maintained. Located just 3 miles upstream on the Capilano River, the 302-foot-high Cleveland Dam creates a storage lake 3.5 miles long and half a mile wide, which provides a usable storage of 12.5 billion gallons of water. Unlike the Seymour River, where the fish spawn below the dam, Capilano River fish spawn above the dam. To ensure they reach their natural spawning grounds, a special fish trap and tank truck system has been developed to move them around this huge man-made obstruction. To meet the demand for water at peak periods, reservoirs are located at strategic points throughout the Greater Vancouver Water District. The Little Mountain Reservoir, which is one of the largest in the system, holds 30 million gallons of water. Originally built in a rock quarry located on a high promontory near the center of the city, this reservoir has been improved over the years. Now it is being completely covered in to protect the water from airborne pollution. To keep the water flowing, pumping stations are located throughout the system. The Vancouver Heights pumping station is one of the high-capacity installations capable of moving millions of gallons of water per day. The station has 2 electric and 3 diesel units, each capable of pumping 10 million gallons per day, for a total of 50 million gallons. Throughout the day and night, there is a continuous demand for water, and the intricate system of reservoirs, dams, mains, and pumping stations are at work around the clock to ensure a dependable supply wherever it is needed. Some pumping stations are underground and operate automatically, cutting in their pumps to meet the constantly fluctuating demands. At times, it is necessary to reroute the flow of water when a pumping station, reservoir, or main is taken out of service for routine maintenance or repair. Without pause, full service continues through supporting facilities. When pumping stations are working on automatic, information is either picked up by closed-circuit television for local control or is flashed to the North Vancouver Master Control Center, which is the heart of the entire water distribution system. Data from the pumping stations located throughout the water district is fed electronically to the Master Control Panel. This information is checked by specially trained operators 24 hours a day. While the outlying pumping stations adjust to local consumer demands by turning on or turning off their pumps, the Master Control Center can, when necessary, take direct charge by overriding their automatic pumping equipment. Water flows in millions of gallons per hour. Water main pressures, reservoir levels, suction and discharge pressures are kept under constant scrutiny by both manual and electronic equipment. This is the nerve center of the entire operation, Trouble. The operator immediately examines the electronic control panel to determine the cause of the alarm. The light on the panel indicates there is a pump malfunction at the Burnaby Mountain pumping station. With the pump out of action, the water pressure in that area will drop. By pushing a button, the duty operator starts a backup pump, and within seconds, full service is restored at the pumping station miles from the control center. This sophisticated system is the result of detailed planning by the Administration Board of the Greater Vancouver Water District, its administrators, engineers, and analysts. Within this building, the watchword is purity of product, for water is a food. Every day, water samples are brought in from 30 testing stations, and these are subjected to tests to determine the chemical and physical quality of the water, including its taste, odor, and visual appearance. The laboratory is concerned with 3 major segments of the water system. First, water at source, the full protection of the mountain catchment areas. In the interest of purity, the general public is not permitted to enter these areas, and water district personnel are subject to rigid medical examinations. Second, the laboratory is concerned with water en route from source to consumers. This involves design of equipment and materials used in pipes, pumps, gates, valves, and buildings. Even paint used by the maintenance and operating department is subject to rigid laboratory test. And third, storage of water at reservoirs to ensure that water is free of contamination and airborne pollution. Because design of equipment and the materials used in its construction can influence the purity of water, the laboratory works very closely with the engineering department, which is responsible for the design and location of new facilities, as well as the production of statistics used to determine the probable need for future expansion and construction. Every year, new projects are phased into the overall Water District program to meet the ever-growing demands of domestic and commercial consumers and to improve present facilities. The Greater Vancouver Water District is managed by a commissioner who is subject to the authority of an administrative board composed of representatives from all member municipalities. The board meets regularly to approve proposed expenditures, authorize developments, and inspect the facilities for which they are responsible. Water is a product, the most inexpensive processed product delivered directly to a consumer. At any given moment throughout the day or night, millions of gallons of water are flowing through Water District and municipal mains, and every hour, millions of gallons are expended in the service of citizens who live within the Greater Vancouver Water District. Water is used, and it flows away to the lands, the lakes, the rivers, and the seas, to be drawn up as vapor to form the clouds that move above the earth, to be released as rain or snow, and it returns again. The eternal cycle continues, for without it, there can be no water, and without water, there can be no life. Unto the place from which the rivers come, they shall return again.